advantage of this type of operation mode is running out of is that the operation cost is low. Okay, and another type is kind of like also common. Okay, it's called what we call the on-demand transit. Okay, they don't have a fixed route. They don't have a specific timetable. They adjust their route and timetable according to the demand. Okay, if the demand at this moment is pretty high, they're going to dispatch more buses. Okay, and furthermore, if there are some demand at particular location, they're going to detour to pick up those customers and by changing its route. And it actually provides a door-to-door service. So the passenger, they don't need to walk. Okay, it offers a high flexibility. However, its operation cost is in general high. And that's why the on-demand transit is not that popular. And many, as far as I know, many on-demand transit companies, actually they did not make any profit and they're bankrupt, okay? Especially in the US, okay? And then the question is that, is it possible for us to design a new transit operation mode which can combine the advantages of these two traditional operation modes? At the meantime, it can enjoy low operation cost, and also it can provide a high flexibility to the customers. Okay, is it possible? This is one figure I copied from Professor Cedar's paper. So the idea is that a fleet of bus with small capacities can be dispatched to provide on-demand service for rural areas, for example, like this one, or small areas. Okay, these are small buses. Okay, why transits, or maybe transits, it doesn't matter. Okay, with high capacity, like this one. Okay, can provide interzone service. Okay, or long distance service. Particularly, the operations of the intra-zone and interzone service are synchronized as this one, okay? Such that the passengers can make the transfer seamlessly, okay? The idea is simple, okay? But it's difficult to realize such an idea in the real world, okay? Particularly, it's rather difficult to synchronize different types of transportation modes, I would say. Okay? And recently, there is a type of technology, okay, called modular autonomous vehicles. It was developed by the Next Future Transportation Company. And the pilot tests have been launched in Dubai a few years ago. Okay? This type of modular vehicles can couple and decouple when they are moving on the road, like these two figures shows. When they are coupled, the doors between them are open, so that the passengers can make emotion transfer. Okay, it means that we don't need to take the transfer. When we get off the bus. Okay, we can make a transfer when the vehicle is moving on the road. Okay, and it can offer efficient and flexible use of capacity, of course, okay? If the capacity, for example, if the demand is pretty high, then we can couple more modular units into a long platoon, okay? And if the demand is small, we can use, for example, maybe a single pod, okay? So that's the idea, okay? Or then I'm going to introduce how this type of technology can facilitate the idea proposed by Professor Cedar. Okay, but before that, I would like to highlight some of the major research gap. Okay, a few researchers have conducted an overall cost effectiveness analysis that comprehensively evaluate the cost and benefits of adopting the MAVs in transit systems. Okay, Professor He Ye's former advisor, okay, also could be one of the first researchers to investigate modular autonomous vehicles in the transit system, okay, Professor Xiaopeng Li, okay. But they are doing kind of like the operation level optimization, okay. But none of them have ever answered the question in terms of the cost effectiveness, okay, of the modular-based transit compared with the two modes that I mentioned, okay, the fixed route transit system and the on-demand transit system, okay. No, none of them have ever done that. So we identified the gap and we would like to fill the gap, okay. So we are gonna develop a comparable continuum approximation models for an MAV-based transit system, as well as two conventional transit systems I just mentioned, okay, fixed route service and on-demand service, to see how MAV-based transit systems can combine the advantages provided by these two conventional transit operation modes and beat them, okay, in real-world operation. So, however, developing such a model is not trivial, okay, because the model needs to incorporate the key features of the modular transit systems, okay. I'm going to introduce these features one by one, okay. The first one, okay, is the stopless or seamless transit operation enabled by the in-motion transfer, okay. If you look at this picture, when the platoon is approaching to a bus station, the vehicles, passengers on board whose destination is here, is at this station, they're going to be moved, they're going to be transferred to the last modular unit or last few modular units, okay? And then this modular unit is going to detach from the platoon, okay? And park at this station to drop the passengers on board. And at the meantime, to serve as a boarding port to pick up the passengers coming later, okay? And for the former boarding port, this one, the purple one, okay? This is the former boarding port detached from a former platoon, okay? It already, with the passengers already on board, okay? When this platoon pass by, it will depart from the station, okay? And then merge with the platoon, okay? And then serve as a holder unit, okay? As you can see, the passengers on board here, okay? They suffer no dwell time. They don't need to suffer. I mean, the traditional bus, they need to stop at the bus station to drop off the passengers and to pick up the new passengers, right? But for the modular vehicle, no, they don't need to suffer any dwell time. So that's what we call the stopless or seamless transit operation. The second feature is the dynamic capacity. I mean, this is easy to understand because by couple and decouple, the capacity of the platoon can be changed, okay? Pretty flexible. And the third feature is the pickup and delivery with reduced detour. It means that a few modular units can be dispatched to provide the pickup and delivery service in rural areas and merge into a long modular transit after the pickup and delivery service. As a result, the detour can be reduced, okay? Because in the rural area, the demand is not that concentrated, okay? Consider that if you use a bus with a high capacity to pick up those passengers, it's gonna create lots of detour. However, for the modular vehicles, it's not the same, okay? We can detach small units, and each unit just to serve one or two passengers, okay? Pick up, and then the others pick up, and then they meet in the corridor, and then merge as a long platoon, and then conduct a long distance travel, okay? By doing that, it can reduce the detour cost. The fourth feature is the synchronization among the MAV platoons. So we want to guarantee that the platoons, when they meet with each other at the intersection, they can exchange their modular units. Okay? For example, some vehicles, the passengers on this modular unit, it may want to go straight forward. Okay? This one want to turn right, this one want to turn left, right? And then they can meet together. They can be detached at the intersection, and at the meantime, okay, for the modular units going to the same direction, they can merge as a platoon. Okay? So it requires the synchronization. Okay? They need to meet each other at the same time, at the same location. Okay? That's the fourth feature. So how can we develop a model to capture all these four features? Okay, it's rather difficult, I would say. So we start, at least for our study, we start from a simple setting. Okay? The surface region is a rectangle. It's a unit width and length of eta. So this is eta. Eta is greater than, is not less than 1. Okay? And then we assume that the demand and origin are static and homogeneously distributed. We use lambda to indicate the demand rate. Okay? And the distance, the destination, we also assume that they're homogeneously distributed. And we adopt the Manhattan distance to calculate the distance matrix. And in terms of the cost, okay, we consider the user costs as well as the agency cost. For the former, it contains the passengers' walking cost, waiting cost, and also the travel cost on board. Okay? And we first developed the model for the fixed route service because some of its derivation will serve as the basis of for the MAV-based model. Okay? The fixed route transit corridor lies in the center of the service region and provide bidirectional service. Okay? And the service region is divided into zones. Okay? And a bus station is located at the center of each zone. Okay? So we define capital L as the length of each zone. Then we have eta is equivalent to the multiplier to the n multiplied by L, capital L. Okay? So it means what? It means, hey, if a passenger generated here, okay, and want to travel to zone 2, then it needs to walk from its origin to the bus station, okay, and aboard. And then we drop off at station 2 and then walk to his or her final destination, okay? And for the intra-zone demand, for example, passengers' origin and destination are in the same zone, okay? Then we assume that they walk to their destination, okay? They cannot take the bus, okay? I mean, that's pretty reasonable, right? Because no bus can help them can pick the passenger to the destination in the same zone, okay? So we define the operating headway as H, okay? So that's the setting for the fixed route service. Questions? And then, given such a simple setting, we can derive the walking time, waiting time, travel time, everything, actually, okay? For example, for the walking time, because as I mentioned, the intra-zone demand, okay, we can calculate by this one. This is to measure, it's just a simple estimation to calculate the average distance between any two nodes within the same zone, okay? We calculated this one. VW is the walking speed, the average walking speed, okay? And the demand is lambda multiplied by L, okay? It's easily calculated based on the assumption that the origin and destination, they are distributed homogeneously, okay? So we can calculate that, okay? And for the inter-zone, the demand, okay, this is the demand. And this is the average walking distance, walking time, okay? L plus 1 divided by 4 and multiplied by VW. VW, as I mentioned, is the average walking distance. So this term is actually measure the average distance, okay, or the average walking time from one point in the zone to the central point of the zone, okay? And we need to multiply by 2 is because when the passenger on board, it need to walk to the station. When the passenger is dropped off, it need to walk from the station to the final destination, and that's why we need to double them, okay? And then multiply by the demand, we have the total walking time. And in terms of the waiting time, because we assume that the headway is fixed, okay, is h, is a decision variable. But anyway, okay, it's divided by h. So the average delay or the average waiting time for one passenger is h divided by 2. Okay, then we can calculate the total waiting time. And for the travel time, it consists of 2 parts. The first part is the cruising time. The second part is the dwell time. For the cruising time, is equivalent to the passenger load on each segment. How to define a segment? The segment, it means that the link between 2 sequential bus stations. So this is segment 1, I would say. Okay, from 2 to 3 is segment 2, and so on. Okay, then for the passenger load on each segment multiplied by the segment cruising time is equivalent to the length of the zone, okay, or the length of the segment divided by VF. VF is the average driving speed, okay? So then how to calculate this one? Actually, I'm not gonna discuss the detail, but as a result, we calculate that the passenger load on segment N can be captured by this term, okay? So we have the cruising time, and it's the same for the dwell time, okay? It's the passenger load on each segment multiplied by the dwell time at each station, okay? Here, the capital D is the unit unit dwell time for processing the one passenger, okay? And then the other term is to measure the total passengers will aboard on that station. And then, because it's a bi-directional service, so we sum them up and multiply by 2, we have this term, okay? And then for the agency cost, is the bus fleet operation cost, okay? Is equivalent to the cost per distance multiplied by the total distance traveled per hour. We convert it into hourly cost, okay? For the first term, we assume it's a linear function in capacity C, okay? It's not a special assumption. It's a well-adopted setting, okay, in the literature. And for the capacity C, okay, for the bus capacity, we want to guarantee no passengers is gonna leave, okay, after the passenger visit the station. It means that the bus capacity should be large enough to accommodate all the passengers. Okay, in order to do that, we figure out that the capacity should be at least this term. Okay, how to calculate this term? This term actually comes from this one, the passenger load on each segment. And when the segment is equivalent to capital N divided by 2, we have this one. Okay, that's the maximum the passenger load. So the capacity should be equivalent to the maximum passenger load. And then the hourly agency cost is nothing, okay? We just use this one multiplied by this term, and that's it. We substitute C, okay, here. So here A and B are 2 parameters. And B, as you can see, is a fixed term, okay? It's a fixed cost. We can interpret it as the crew cost, okay? The driver cost, if it's not an autonomous vehicle, for example, okay? Or anyway, it's a sum cost, okay? And the total cost for the fixed route service is nothing special. It's just a weighting sum of the walking time, waiting time, travel time, and the agency cost. And then we turn to the MAV-based transit system. Similar to the fixed route service, there is a bi-directional interzoned corridor service like this one. Okay? And along the central of each zone being a station, okay? We also have a station concept. And on top of this, the MAV-based service also include 2N unit directional intra-zone pickup and delivery routes, which provide feeder service like this, okay? Provide feeder service between the corridor, the central corridor, and the rural areas of each zone, okay? Here, I want to highlight both the central corridor and the pickup and delivery service. They are all operated by modular autonomous vehicles, okay? And these arrows presents the operation, the direction of each pickup and delivery service. As you can see, okay, they are not equivalent. They are not the same, okay, for different zones, okay. We decided on purpose, okay. I'm gonna elaborate it a little bit, okay. And so along the central corridor, there are 3 rearrangement hubs like this one, this black box, okay. Bus station is a special. It's also a type of hubs, okay, where the modular autonomous vehicles can meet and rearrange their platoons or exchange their modular units with the other modular platoons, okay. That's the purpose. So we define them as hubs, okay. These hubs just a concept. You understand it as a hub. And in reality, it may not be physically that exist, okay? And then I would like to highlight, because those hubs are evenly distributed, okay? So the distance between any 2 sequential hubs, okay, is equivalent to capital L divided by 3, okay? Remember this information. And the corridor operating headway, we define as H hat, okay? That's the one we want to optimize. And further, I'm gonna elaborate the operation at the hubs and the operation in the pickup and delivery routes. So we first look at the zone 1, the first zone. We have the west hub, middle hub, and east hub, okay? Because for each zone, we have 3 hubs, okay? And for zone 1's west hub, if we look at this one first, okay? It's nothing special, okay? It's just a merge of 2 modular platoons or modular units that just finish the northern pickup and delivery service, okay? And they merge, okay? Merge here. And it's gonna go ahead to zone 2 and the other zones, okay? And in the middle hub, if we look at this one, this is a bus station, right? It's a bus station. It's actually a terminal station, okay? The westbound vehicles, like this one, Unit 4, it is already reached the terminal station, so it will turn around and park here, stop here at the terminal station to drop the passengers on board and serve as a boarding port, okay? I already explained what's the boarding port at the very beginning, okay? And Unit 3 is a boarding port. It's from a former platoon, I would say, okay? This is Unit 3, and this is Unit 3, okay? It already finished the drop and pick up service, okay? And when the following boarding port comes, okay, it will depart. When it departs, okay, this platoon, okay, the corridor service, the corridor platoon, like this one, 1, 2, it will pass by the station, okay? And this boarding port 3 with the passengers on board will catch up and merge as a platoon, okay? To provide service, okay? And head to zone 2 or zone 3 and the other zones, okay? On the eastbound, okay? So that's the operation at the middle hub. So in the east hub, okay? When for this platoon, this is a westbound platoon, okay? Because some of the passenger, this is zone 1. Zone 1 is the last zone. It's the left-hand side. the most left-hand side zone, okay? So all the passengers, okay, on the westbound modular proton will need to be dropped off. So some of the passengers will be dropped off on the northern pickup and delivery route. Some of them will be in the southern part. And some of them will be dropped off at the station. So this modular proton will detach 3 different modular units or 3 different modular protons. Okay? One is to provide the drop-off and pickup service, okay, in the north part of the area. Okay? And some to serve the south part, and some, okay, this is modular unit 5. It will behave exactly the same behavior as modular unit 4. Okay? So that's the operation for zone 1. Okay? So questions? I mean, we don't need to wait until the end of the presentation, because if you lose your mind, your focus here, then you may not easy to follow up. Okay? Okay, good. And then for zone 2, okay, if we look at the middle hub first, it's nothing special. Okay, it's exactly the same as the middle hub in zone 1. But because this bus station is not a terminal, okay, so the modular unit, they don't need to turn around. Okay, they just need to park at the station, okay, as a boarding part, and then waiting for the next proton to pass by and catch up. Okay, right? And for the west hub, it's a little bit more complicated. It's an intersection of 3 modular protons. Okay, this one and this one are the corridor protons. Okay, as we can see, when they arrive at this hub, okay, they're gonna detach some modular units. This is modular unit 3. This is modular unit 10 and 11 to provide the pickup and delivery service in the southern pickup and delivery service route. Okay. At the meantime, to pick up, okay, the proton, the modular units just finish the northern pickup and delivery service. You see, some people, they want to go ahead to the zones on the right hand side. So for example, they will be transferred to modular unit 12. Oh, sorry, modular unit 13 and 14, you see, 13 and 14, it will couple with modular unit 1 and 2 and form a larger proton and go ahead to the other zones on the right-hand side, okay? And for some passengers, it may want to go ahead to the zones on the left-hand side because this is zone 2. So for these passengers, their destination must be in zone 1, okay? So they're gonna merge with the modular unit 8 and 9, okay? For the east hub, it's a symmetric one with the west hub, okay? Here, I want to highlight one thing, okay? If we look at the east hub of zone 1, okay, this modular unit 6 and 7, after they finish their pickup and delivery service, they will become the unit 2 and unit 1. And it's a cycle, okay? It will operate forever, okay? So one thing I want to highlight is demand adapted. So here you can see, this is a modular unit, okay? 1 modular unit. But in reality, if the demand is high, it could be 2 modular units or even 3 modular units, okay? It's demand adapted, okay? It's a variable our model can optimize. And given that one, we turn to the pickup and delivery service. And each zone is conceptually divided into a 6x6 grid. And the bus routes operate along the grid line located at 1/6 of the width from the boundary. Okay, if we look at this one, you see. The reason is that the distance between 2 sequential hubs is capital L divided by 3. Okay, and then we can calculate the distance between the hub and the boundary is L divided by 6. That's it, nothing special. Okay, and the service is operated on a flag down or held and ride mode with no predetermined stops. Okay, we don't have stops. It's just, hey, I see a vehicle pass by, I held. okay, and then I abort, and that's it, okay? But the passengers need to walk to the closest pickup and delivery route, okay? For example, if the passenger is here, it needs to walk to this node, okay? And then we turn to the user choice assumption. First, the intra-zone, the travelers are assumed not to use the transit. Okay? Unfortunately, to simplify the model, we do not assume that, we do not allow that the passengers, the intra-zone passengers can use the pickup and delivery to arrive the destination in the same zone. Unfortunately, okay? And for the inter-zone, the users, they are assumed to use the nearest access or egress option. Okay, I'm gonna show you guys. So this is reasonable, right? Because nobody, for the passengers, if they want to hail and ride, okay, definitely they want to find a location which can minimize its walking time, okay, where he or she can hail and ride, right? So it's a very reasonable assumption, okay? For example, in order to calculate or capture this equilibrium, okay, we have to conduct very detailed analysis. For example, we divide the areas of a sub-area of this zone, okay, into 4 types. This type, 4 parts. This part, this 1, 2, 3, and 4, okay? For each part of the passengers where they are generated, we'll figure out that they are gonna walk to, for example, for the passenger generated in this area, it will definitely walk to this point or this curve, okay? For passengers generated here, it will walk to this exactly point, okay? And for the passengers whose their origin is here within this great area, it will walk to the station, the bus station directly, okay? They're not gonna use the pickup and delivery service. And then given that, we can calculate the average walking distance for accessing the MAV-based transit system by DW, and then we can calculate the total walking time, okay, similar to the fixed route service. And for the waiting time, it's exactly the same, okay? It's a 50% of the headway. And furthermore, to guarantee the synchronization such that different modular platoons, they can meet in the same time, in the same hub, okay? We can prove that, okay, the headway should satisfy this constraint, okay? The headway must be 2 divided by 3 RV. So here R is an integer, it's a positive integer. It could be 1, 2, or 3. So optimizing the headway is equivalent to optimizing the value of R, okay? And the time spent for each pickup and delivery route is equivalent to the effective service time plus the waiting time for synchronizing with the corridor. It means that the passengers can wait here, or the modular unit can wait at the hub for the corridor service, okay? So, and we have to guarantee, okay, in order to let the pickup and delivery service or modular units, they can meet the corridor service at the same time. We need to guarantee the time spent on each pickup and delivery route is an integer, okay, multiplied by the headway of the corridor service, okay? Then given that, so we have SH head must be not less than the effective service time, and we can calculate that S, the optimal S, okay, must be equivalent to this term. And then we turn to the travel time. It's a little bit complicated compared with the fixed route service, but the idea is the same. We calculate the passenger load on each segment, okay, and multiply by the travel time, okay? And this is what this is for the pickup and delivery route, okay? We are lucky because the passenger load along the pickup and delivery route is a constant, okay? We prove that it's a constant. And for the corridor, it's exactly identical to the fixed route transit service. And for the agency cost, we adopt similar setting. The only difference is that because the capacity of a modular platon depends on the number of modular units. You cannot say, hey, I just use 1.5 modular unit to form a platon. It must be an integer. It could be either 1 modular unit or 2 modular units or 3 and so on. It cannot be 1.5 or 1.2, okay? So we add 50% of the capacity to measure the average, okay? Then we can calculate the hourly the agency cost at this one, and that's all for the MAV-based transit system. And for the on-demand service, we adopt a no back tracking policy. Okay, the vehicle is not allowed to move back in one direction. This figure portrays a trajectory of a vehicle following an eastbound, no back tracking policy. After you see the vehicle starts from the westbound, okay, and it goes ahead to serve the request to the westbound. After finishing the last request, it will turn around and provide service, okay, to the request, to the passengers, to the westbound, okay? We adopt such a control policy because it can provide a good approximation to an optimal routing heuristic, okay? It has been approved, okay, but not, it has been proven, but not by us, okay? So as a result, we can calculate the working time, waiting time, travel time, and agency cost for on-demand service. So definitely the working time, okay, the working cost for the on-demand service is 0 because the bus is gonna provide a door-to-door service, okay? The passengers doesn't need to walk, okay? They don't have a station concept, okay? And this table actually summarizes each cost components of each operation mode, okay? Then the problem is that we need to conduct analysis based on these results, okay? First, we have several propositions. The first 2 propositions is to identify the closed form for the optimal headway for fixed route mode and the on-demand service mode, okay? We are lucky, they all have closed form, okay? And for the modular autonomous, modular-based system, unfortunately, because the headway is related to an integer variable, right? R, okay? For integer variable, we cannot derive a closed form. However, we can identify the range, the optimal range for the optimal, the range for the optimal R value. And then accordingly, we can calculate the optimal range for the headway. However, though we don't have a closed form, but it does not affect our analytical analysis. So this is the first proposition, okay? You just need to understand the physical meaning, okay? As we extend the transit corridor to maintain optimality for the fixed route transit and on-demand service, we have to increase the frequency, okay? If you are familiar with the transit system, you should understand it. Intuitive, the corridor is longer, then the frequency of the bus should be higher, okay? However, for the MAV-based system, when the corridor is reasonably long, extending it will not raise the need for new headway. It means what? We don't need the additional modular units, okay, to guarantee the same service as the corridor becomes longer and longer, okay? The reason is comes from 2 MAV features. First is the stopless corridor operation. Think about that. For the traditional transit, when the corridor is longer, it means what? There are more bus stations, right? The more bus stations, it means the higher the dwell time delay, okay? The delay due to the dwell time. Because at each station, bus station, they need to stop to drop off and pick up passengers, right? But for MAV-based system, no, we don't, because it's stopless. So no matter how long the corridor is, okay, adding more zones will not affect the performance, right? Secondly, for the pickup and delivery service, as you can see, this pickup and delivery service is operated independently in each zone, okay? Adding more zones will actually the impact of adding more zones is quite marginal, okay, on the operation of the pickup and delivery service, okay? So, yeah. And the second, the sixth proposition is that the per capita working cost for the fixed route transit is increasing in eta. Eta is the length of the corridor. While for the MAV-based system is decreasing in eta, okay? Why? Because you can see if eta is larger, okay, this term is going to be larger. However, for this one, when eta is larger, as long as this is a positive term, okay, and this is the whole term is becoming smaller, okay? And so the reason is that the dW is smaller than this term, okay? The physical meaning, the insight is that dW actually represents the transit access cost, the average walking distance, if you still remember dW's physical meaning, okay, should be known enough such that the walking cost enjoys the economies of scale for longer transit corridor, okay? This is important, but for traditional transit system, unfortunately, the fixed route, unfortunately, it does not fulfill this requirement. And the seventh proposition is that as long as this inequality can be fulfilled and the sum of walking and travel cost for the fixed route service will always be greater than the MAV-based service. And we validate it, okay? This inequality condition will always be satisfied, okay, based on the real-world parameters, okay? It means what? It means MAV-based service can always beat the fixed route service in terms of the walking and travel cost. And because I don't have much time, so I'm gonna quickly go through it. So suppose that the government is not that rich, okay? They want to use the minimum, the budget, to maintain the service, the transit service, okay? But they don't care about the user's experience. For example, the user's waiting time could be pretty high, okay? But I don't care. As long as each passenger can be served, that's it, okay? We divide it as a minimum required budget. We can figure out that, hey, the modular, the on-demand transit, okay, the budget for the on-demand transit is the highest, okay? And this is so it demonstrates or it echoes the second slide that I highlight. The on-demand transit may suffer high operation cost compared with the fixed route transit system, okay? And then under certain condition, okay, the modular, the MAV-based transit system, okay, can yield a budget even smaller than the fixed route transit service, okay? And this condition emphasizes that high demand and autonomous driving favor the MAV-based system, okay? Yeah, the last two slides, okay? And suppose the government is super rich, okay? I'm not sure, okay, for Jeju could be like that, okay? The government, they have lots of budget. They don't care about the budget, but they want to improve the users or passengers' experience, okay, by minimizing the user's cost. Then given a same budget B, okay, we'll figure out that if the budget is sufficiently large, okay, then on-demand service is the best, okay? And the fixed route transit, this is the fixed route transit. The higher, the worse, okay? The fixed route transit is the worst, okay? And the on-demand transit is the best, okay? And modular transit is somewhat in between, okay? The reason is that when the budget is large enough, the on-demand service will be the most user-friendly mode because the on-demand service has zero walking cost, while the walking cost for the other two modes cannot be reduced, no matter how large the budget is. Anyway, for a fixed route service, no matter how small the frequency is, okay, the walking distance cannot be minimized to zero, okay? Okay, the last slide, okay. This figure shows, hey, the user cost when the corresponding to different budget, okay? And the blue curve shows the fixed route, okay, transit system. This one is the MAV-based, and the green one is the on-demand, If you look at this one, you figure out that when the budget is pretty high, okay, you should adopt on-demand service, right? When the budget is pretty small, you can only consider the fixed route, okay, transit system, okay? But if we look at this period, okay, it shows us when the budget is moderate, okay, the MAV-based system actually can add to the spectrum of the transit operation modes as an effective complement to the existing ones. Because you see, without the modular autonomous vehicle transit system, when the budget is within this area, the only option is fixed route, okay? But the user cost is pretty high, right? But with the presence of the modular autonomous vehicle, the user cost has been dropped significantly, okay? So, yeah, that's all I would like to share with you guys. Yeah, thank you very much.